All right, today we're going on a quest. We're not looking for lost treasure or anything like that. We're looking for something way more valuable in our world, the perfect algorithm. It's this invisible engine running pretty much everything you do. So let's dive in and figure out what really makes one great.
Okay, so what is an algorithm really? The best way to think about it is like a recipe. A step-by-step guide to get something done, whether that's baking a cake, sorting 1,000 names alphabetically, or finding the absolute fastest way for you to get to work. It's just a set of instructions. And this is where it gets really interesting. For any problem, there isn't just one recipe. There could be dozens, maybe even thousands of different ways to solve it. So, how on earth do you even begin to pick the best one? Which recipe wins?
So, how do we choose? Well, the first thing you have to get is that just getting the right answer, that's not enough. Not even close. That's like the bare minimum. That's just table stakes. The real art is in finding a recipe that does so much more.
See, the real goal is to find an algorithm that hits two marks. First, it has to be correct. It has to work every single time. But second, and this is the big one, it has to be efficient. And that second word, efficient, man, that's where the real quest begins.
To figure out which one is the most efficient, we need a way to measure them, a way to score them against each other. So you can think of it like we have this official scorecard that we use to judge every single recipe on its own merits.
On our scorecard, there are two scores that matter more than anything else. First is time complexity. Let's call this cooking time. We're not literally talking about minutes and seconds, but about how much longer the recipe takes if you suddenly have to cook for 1,000 people instead of just 10. Then we have space complexity. Think of this as your counter space. How much memory, how much room does the algorithm need to do its job as the problem gets bigger?
But the scorecard doesn't just stop there, oh no. We're also asking other questions. How simple is this recipe? Is it easy to read and understand? How well does it scale? Will it completely fall apart with a huge amount of ingredients? Is it robust? What happens if you put in the wrong input by mistake? And can you adapt this recipe for other similar dishes? All of this stuff factors in.
It really all boils down to this one simple idea. Getting an answer is easy. Anyone can do that. But getting the answer fast, especially when you're dealing with mountains of data, that is the real challenge. That's what computer science is all about.
Okay, but hang on a second. This brings up a huge problem. How do you test these recipes fairly? I mean, my brand new laptop is going to run any recipe way faster than my 10-year-old computer. We need a totally level playing field to get a fair score.
So the real question is, how in the world can you test an algorithm's speed and efficiency without the whole test being biased by the specific computer you're running it on? How do you make it fair?
And the answer is actually kind of brilliant. You don't use a real computer at all. Instead, computer scientists invented something called a model of computation. It's basically a theoretical computer, an imaginary one that's perfectly predictable and ensures every single algorithm is tested under the exact same fair conditions.
And there are actually a few different models for different jobs. You've got the famous Turing machine, which is all about the theory of what's even possible to compute. You have the quantum model for, you guessed it, quantum computers. But for almost all the practical stuff we do every day, the undisputed champion is the RAM model.
All right, so let's step inside this virtual machine. Meet the RAM model. This is our standardized test kitchen, and it has a very specific set of rules that everyone in the field has agreed to follow. Okay, so here's the official textbook definition. The random access machine, or RAM model, is an abstract machine that we use to get a realistic analysis of an algorithm's time and space complexity, completely detached from any real-world hardware.
And here are the simple rules of the road that make this whole thing fair. In our virtual test kitchen, memory is infinite. We never run out. Getting any piece of information from memory takes the exact same amount of time, no matter where it is. And every basic simple instruction, like adding two numbers, costs exactly one tick, one single unit of time.
Okay, I know that sounds super abstract, so let's make it real. Let's see it in action with a super simple example so you can see exactly how we use this imaginary machine. Let's say our job is to add up a list of numbers. Let's say there are n numbers in that list. So in our RAM model, we just count the steps. Setting our starting total to 0, that's one step. Then we have to look at each of the n numbers, and for each one, we do an addition. The key thing here is that as n, the number of items, gets bigger, the total number of steps grows right along with it, in a straight line. In computer science, we have a name for this kind of growth. It's called Big O notation. We'd say this algorithm is O of n.
And that right there is the most important thing to remember from all of this. Algorithm analysis is never about measuring raw time, like in seconds or minutes. It's about understanding how the performance scales as the problem goes from, say, 10 items to 10 million. That's the difference between a good algorithm and a truly great one.
Seriously, think about it. From your GPS to your music recommendations, your entire world is powered by these competing recipes. And now you know the secret scorecard that we use to decide which ones win the race. It kind of makes you wonder, right? What's one algorithm in your life you wish was just a little more efficient?